Hi everyone, and welcome to this next session on basic antiderivatives. Recall that from the fundamental theorem of calculus, we have that if a function f of x is continuous over the interval ab, and if big F of x is any antiderivative of little f of x, then the definite integral from a to b with little f of x as the integrand can be computed by finding an antiderivative, big F of x, and computing its values at b and a, and finding the difference between these values. You'll quickly realize that to apply the fundamental theorem of calculus, you'll have to first and foremost be able to find a function's antiderivative. So in this video, we will focus strictly on the operation of finding an antiderivative, which we call antidifferentiating, or doing an indefinite integral. By definition, big F of x is an antiderivative of little f of x if big F prime is equal to little f. Basically, finding an antiderivative means doing the reverse operation that had been done in Cal 1, which was the differentiating process. In other words, when we differentiate x cubed plus 3x squared plus some constant to get 3x squared plus 6x, then the reverse operation is called antidifferentiating. So the antiderivative of 3x squared plus 6x is x cubed plus 3x squared plus any arbitrary constant. In terms of notation, when we differentiated functions in Cal 1, we used the prime symbol or the Leibniz notation d dx. In Cal 2, we will use the integration symbol, so the elongated s, but with the absence of bounds this time. So the integral, or the indefinite integral of little f of x, acting on 3x squared plus 6x, reveals an antiderivative, x cubed plus 3x squared plus k. So without bounds, the integration symbol is simply an indication that we are looking to antidifferentiate the integrand. The elongated s will now play the role of the antidifferentiation symbol, or the indefinite integration symbol, and dx is the antidifferentiation variable. If the function had no x's within its expression, then it would be simply a constant. Here is the list of basic antiderivatives that you will need to know and use in order to proceed with integration in the future. First and foremost, the antiderivative of 1 using dx as the integration element is x plus k. You will convince yourself this rule is true if you take x plus constant, differentiate it, and obtain 1 as an answer. So you can always verify doing the reverse operation that your rules are true. Here's why we see whereas we see the importance of the dx symbol. If this were an integral of 1 dt, then the antiderivative would have been t plus k. The integral of 1 d theta would have been theta plus k. So dx is just a reminder of the variable the function depends on. For any value of n that is not minus 1, then the rule for powers of x, x to the n, is x to the n plus 1 over n plus 1, with the addition of an arbitrary constant. You see that n cannot be minus 1 in order to avoid a division by 0. So this is the power rule, and its expression kind of makes sense because in Cal 1, you would have learned that differentiating would reduce the power of the exponent, and in this case, we are adding 1 to the power of the exponent. Rather than the exponent becoming a coefficient, in this case, we have the new power becoming a divider. Again, if you differentiate x to the n plus 1 over n plus 1, you will verify that the rule actually fits because x to the n will be the outcome. For instance, here's how we can apply the power rule. If we integrate x to the power 3, well, according to the power rule, we would add 1 to the exponent, so making it 4, and divide by the new exponent. So x to the 4 over 4 plus any arbitrary constant. By the way, the derivative of x to the 4 is 4x cubed. Divided by 4 will give you x cubed. That's a way to verify that you've applied the rule correctly. Be careful not to use the power rule directly with expressions such as 1 over x squared, because here the rule does not apply to 1 over x to the n, but to powers x to the n. So we'll actually do a first step of reversing the fraction and writing it as x to the minus 2. This now has the form x to the n. And the power rule for anti-differentiating tells us to add 1 to the exponent, so it will become x to the minus 1 over the new exponent, which is minus 1. It's worthwhile to rewrite this end result so that negative exponents no longer appear. So perhaps minus 1 over x plus an arbitrary constant is a better way of writing this final answer. As usual, differentiating minus 1 over x plus k should bring you back to the starting integrand, which is 1 over x squared. Likewise, for roots, perhaps a good intermediate step is to rewrite as a power. So x to the 1/3 can be written as an equivalent way of writing the cube root of x. The power rule forces you or suggests to add 1 to the exponent, so 1/3 plus 1 is 4/3, and 4/3 also becomes the denominator. So x to the 4/3 over 4/3 plus an arbitrary constant, or you could also write this as 3/4 x to the 4/3 plus a constant. These are all applications of the power rule. In the remaining list of our basic antiderivatives, we have, for instance, 1 over x, whose antiderivative is ln of x. I've incorporated the absolute value of x simply because of domain purposes. 1 over x is a function that exists both for positive and negative values of x. Ln only exists for positive arguments, so we need to make sure that the content of the ln is positive. The added arbitrary constant, always worthwhile to include. Here's your favorite formula. The antiderivative of e to the x is e to the x, simply because the derivative of e to the x is e to the x. For more general exponential functions, if the base is different than e, like 10 or 2, then antidifferentiating a to the x is a to the x over ln of a. The antiderivative of cos of x is sine of x, because the derivative of sine of x is cos of x. So if you're confused with the sign, differentiate your end result, see if you are back with the original integrand. The antiderivative of sine of x is minus cos of x. The antiderivative of secant square x is tan of x, because as you've learned, the derivative of tan x is secant square x. As usual, plus k's, arbitrary constants are added just for generalization of all possible antiderivatives. Not used quite as much, but I'll still mention them. So the antiderivative of cosecant square x is minus cotan of x. The antiderivative of secant x tan x is secant x. And the antiderivative of cosecant x cotan x is minus cotan of x. All of these rules are simply adapted if the variable names are changed. So if x's become t's, all of these rules still apply. Last but not least, we have the inverse trig functions. I've presented them in a slightly more general way than we have seen when we differentiated the inverse trig functions themselves, just to make it easier to generalize. So the antiderivative of 1 over root of a squared minus x squared is arc sine of x over a. Keep in mind here, a is a constant, whereas x is a variable. And how do we know x is a variable? That's why there is the dx symbol. Dx is there to remind you that that is the variable being integrated. 1 over x squared plus a squared is antidifferentiated to produce 1 over a arc tan of x over a. Note that, as it was the case for definite integrals, the constant multiple and the sum difference rules and properties can still be applied. So constants can be removed from an antiderivative, just like an addition or a subtraction of two functions being antidifferentiated can be converted into the addition of the individual antiderivatives, or their subtraction, depending on the situation. For example, the antiderivative of 4e to the x is equal to 4 times the antiderivative of e to the x dx. Our basic rules tell us that the antiderivative of e to the x remains e to the x, so 4e to the x plus k. For one given antiderivative, it's fine to just incorporate one arbitrary constant at the end. The antiderivative of 3 cos of x minus sine of x dx, using the difference rule, allows you to split it up into two different antiderivatives. The constant multiple 3 can be extracted, and you'll notice the two remaining antiderivatives fit the basic rules we've seen. So the antiderivative of cos of x is sine of x. The antiderivative of sine of x is minus cos of x, which will cause a change in signs. And since the antidifferentiation process is now done, we'll add an arbitrary constant.